right, we are covering derivatives in Unit 2. There are a lot of rules that we're going to be learning here. But the first thing we have to do is learn about what a derivative is. And a derivative is the slope of the tangent line. So the slope of the tangent line is called derivative. So we're going to start with a function here, y equals f of x. And to get to the slope of the tangent line, we're going to start with some points here. I'm going to pick a point. X value is x. Y value then, plug x into the function, is f of x. Okay, and then we can also label our coordinate pair. Next thing that happens, we're going to find another point here. What we've done is we have moved over on the x-axis some distance. We'll call it delta x, sometimes h, but delta x for now. So now, what is our x value? So this x value is x plus delta x. And its corresponding y value, if I plug that into my function, is f of x plus delta x. And I can also label this point. So what we can do through any two points, is draw a line. And when we have a line that goes through two different points, this is our secant line. We're going to start with the secant line. And over here, we're going to talk about the slope of this secant line. So how do we calculate slope? Our slope formula, just difference of the y's over difference of the x's. So I'm going to take my points here, and we're going to do the difference of the y values over the difference of the x values. Okay, and you might notice that the denominator will simplify. And that's the slope of the secant line, which is just slope through any 2 points. We'll also use this slope through 2 points as an average rate of change. So you may have heard that this is called the average rate of change. That will come up. We talk about the average rate of change on an interval, let's say AB. And so our slope here would just be difference of our y value, f of b minus f of a, over b minus a. So kind of a lot of stuff here. Slope of a secant line is the slope through 2 points. It's our average rate of change on an interval. And this is what we end up with here. Okay, well, we still have to talk about the slope of the tangent line. We're trying to get to the derivative. So we need a tangent line, not a secant line. What's going to happen now is we want to take this point here, we want to slide it along our function until it ends up on top of this point. And then we'll have a tangent line at that one point. Okay, so if we do that, we're going to end up with this line here. This is our tangent line. We only touch the function at one point. We're going to go over here and talk about the slope of this line. Right. So what did we do to get to this line? We took this point, we split it along our graph until it ended up here. And what happened was at that same time, our distance delta x, it got smaller and smaller and smaller. And we know that when something's getting smaller and smaller, the value is approaching 0. And when we talk about what something is approaching, we're talking about a limit. So this definition involves a limit as delta x approaches 0 of simply the slope of our secant line. So it doesn't look very pretty or very friendly, but that's all right. This is the slope of the tangent line, which we also call the derivative. Okay, the derivative is going to be written this way. So if this is function f, our derivative is called f prime of x. Okay. So it's the derivative of f. Back over here on the slope of the secant line, we note that it was called the average rate of change. The slope of the tangent line is a rate of change at one point, and so it is called the instantaneous rate of change. And those words are important to remember. When you're asked to find the average rate of change, you're asked to find the slope through 2 points. When you're asked to find the instantaneous rate of change, you're being asked to calculate a derivative, or the slope of the tangent line. So here's our first example. We're going to let f of x be 4x minus x squared. I'm going to ask you to do several things. The first thing is find the derivative of f by using the limit process. So this whole unit is about learning the derivative rules and the shortcuts, but we're not there yet. You probably remember doing this a little bit last year at the end of the year. So what we want to do now is to find the derivative of f. We want to remember that this is f prime of x, slope of the tangent line. So using our definition up here, f prime of x, the limit, and I'm going to change delta x to h as h approaches 0 of f of x plus h minus f of x all over h. This is our definition. This is what we'll start with each time we have to use the limit process. So this is the limit process. This is the definition of the derivative right here. And then we're going to start plugging things in using our specific formula. So we have the limit as h approaches 0. Then here we're going to fill in these pieces. So easy things, divide by h, fill that in. We have a little bit of subtraction here, and it's going to end up a little bit back here. Okay. Real easy part, back here what follows the subtraction sign is f of x. So you can go ahead and plug in the function following the subtraction sign. We're just going to use parentheses. Okay. And then in front, it's our function, but instead of x, we have x plus h in place of all our x's. So in place of this one and this one here, we have 4 times x plus h minus x plus h squared. Now it's up to us to just work this out. So some algebra here. Remember, as you do a limit problem, to continue writing the limit condition at the beginning. Okay, we're going to work this out. 4x plus 4h. Here, you want to be really careful to square x plus h. And if you want to distribute the negative as you go, make sure you do that. So x squared minus x squared. Then we'd get xh twice. Distribute the negative would be minus xh. And then we get h squared, and we distribute that negative. Okay? Minus 4x plus x squared. And it's all divided by h. So again, this is just some algebra cleanup here. We're looking for values that will drop out. So there's several. We can get rid of x squared terms, or x terms, and everything else, you'll notice, has an h remaining inside. So my next step, I'll go ahead and factor that h out. Okay, here I'm reducing, so h over h. Now it's safe to plug in 0 for any remaining h in the problem, which would be this one here. And we're left with 4 minus 2x. That might surprise you. Maybe you were expecting an answer like 4 and not something with a variable in it. And that can happen. Most of the time we get answers like this. This is our slope function, 4 minus 2x. So this is the derivative of 4x minus x squared. 4 minus 2x is the derivative. Okay. We're going to talk about why it has an x in there. So part B, we're going to sketch this function. Okay, so we have a parabola here. And easy way to sketch a parabola like this, factor out an x. We're left with 4 minus x. So I can sketch by using my x-intercepts 0 and 4. Okay, right in the middle should be the vertex at 2. And if we plug 2 back into our function here, we'll find that it happens at 2, 4. So vertex 4 opens down. That x squared was negative. Okay. And what we did was we found the derivative. Well, the derivative is the slope of the tangent line. And we didn't find the slope of the tangent line to a specific place on our curve. That's why we're getting this 4 minus 2x. It depends on where we look. So if I want the slope of the tangent line over here when, say, x is 1, I'll get 1 slope. If I want to know what the slope of the tangent line is when x is 2, I'll get a different slope. So it depends on where we are, which is why there's a variable here. It depends on what x value you want to plug in. Let's look at part C. Write the equation of a tangent line to this function when x is 5? Well, there's two things that we need to know to write the equation of a line. Okay, those two things are point and slope. So for my point, I know x has to be 5. So 5 what? So to figure out the point, it's a point on my function. So I want to plug 5 back into the original function. So f of 5. So we're going to get 20 minus 25 is negative 5. As for the slope of this line, when x is 5, okay, again, I want the slope of my tangent line, while the derivative is the slope of my tangent line. So I'm going to plug 5 into my derivative function, f prime of 5. So I'm going to get 4 minus 10, which is negative 6. And that's all I need to write the equation of a line, a point and my slope. So y minus negative 5 equal to negative 6 times x minus 5. In our second and last example, we're going to find the derivative of a rational function, 2 over x plus 1, by using the limit process. Again, the derivative of g, the g prime. Using our definition, we have the limit as h approaches 0 of g of x plus h minus g of x all over h. So we're going to start by filling this in here using our new function. Remember to write that limit out front. On the bottom, of course, we're just dividing by h. Now on the top, g of x plus h. We want to plug x plus h in place of the x. So this will become an x plus h plus 1, 2 over x plus h plus 1. Then we subtract g of x, which is just our original function, 2 over x plus 1. Okay. What we ended up with here is a complex fraction. And to simplify complex fractions, we need to multiply by the least common denominator. So we're going to need an x plus 1 and an x plus h plus 1, both on the top of our complex fraction and on the bottom of the complex fraction. So our limit as h approaches 0. So on the top, we'll go ahead and distribute. So the first terms are gone. We're left with 2 times x plus 1, and we can distribute that as we go. So that's going to give us 2x plus 2. Okay, we've got to be really careful here. Distribute to our second term. The x plus 1s are gone. We'll distribute negative 2 to x plus h plus 1. In the denominator, there's no fraction here, right? So we just want to leave these factored here and not multiply anything out. On the top, we clean up. We're going to eliminate 2, negative 2, 2x, and negative 2x. The only thing I have left now is a negative 2h. I'm going to go ahead and rewrite this just so it's a little clearer to see. Just a negative 2h. Remember, if you were to plug in that 0 right now for h, you would still get 0 divided by 0, and it would appear like there is no derivative. but there is. So we still want to reduce those h's here. So that's why I rewrote that. Leaves -2 in the numerator, and now it should be safe to plug in 0 for any remaining h, which would just be here. We're left with -2, x plus 1 times x plus 1 would be x plus 1 squared. So that's it. That's our derivative. So just like last time, a few more things to do here. First of all, I want you to sketch the function. So sketch the original function. Okay, and g of x is a rational function, 2 over x plus 1. So we just reviewed this in Unit 1. So we have some asymptotes here. Remember that it's bottom heavy, so we have a horizontal asymptote. As far as x-intercepts go, there's no way to make our fraction equal 0, so we won't have one. And for my y-intercept, if I plug in 0 for x, we'll get 2. So we're going to sketch this now with our information. All right. Vertical asymptote when x is -1. Horizontal is right here on the x-axis. No x-intercept, and a y-intercept of 2. All right, so the piece on the right side of the vertical asymptote is going to cross through 2. And the piece on the left side, if you're not sure, remember you can always plug in a value. So the vertical asymptote is at -1. You can plug in -2 if you want to see where this is. So g of -2 would give us 2 over -2 plus 1. Gives us -2. We have a point here. This piece is underneath the horizontal. So there we go. There's our rational function. Part C, one more thing here. Write the equations. There are 2 this time. For the tangent lines. That have a slope of -2. So instead of giving you, like in example 1, an x value, this time we're telling you a slope value. So we need to find out when our function has a slope of -2. Okay, so we take our slope function here, way back here. This is our slope function. This is what we want the slope to be. So we're going to set the 2 things equal. Okay, we'll go ahead and solve for x. So if I have -2 is equal to -2, x plus 1 squared is equal to 1. We get x plus 1 must equal plus or minus 1. And so we subtract 1 from each. 1 minus 1 would be 0. -1 minus 1 would be -2. So these are the x values. So I have the 2 lines. They each have a slope of -2. But the 2 lines touch at 2 different points on our graph. So one of them happens when x is 0. One of them happens when x is -2. So if we're looking for points on our function, we want to make sure we plug these values back into the original function to find those points. So we have g of 0. That's going to give us 2 over 1, 2. and g of negative 2, which earlier we actually did already, is negative 2. So we have 2 points, and for both of them, we set a slope of negative 2. We want to write the equations for these two tangent lines. So there's 2 lines, 2 equations. So the first one goes through 0, 2. That's y minus 2 equals negative 2 times x minus 0. So I'll just write x. And really we could simplify this to y equals negative 2x plus 2. So there's one tangent line. And then we have one more going through negative 2, negative 2. So y minus negative 2 is equal to negative 2 times x minus negative 2. That one I'll just leave. So there are our two tangent lines.